Hi there everyone, it's Mr. Erickson here. We're going to be talking, going to be doing some demonstrations here for you. We're going to be doing some stuff here. I'm going to show you some stuff, uh, um, uh, go over some concepts, and then I have a challenge for you at the end. Before I do that, I want to go over some of your answers from the Forces in Motion video question. The first question was, which of these are not applied forces? And I listed a bunch of them there. Go ahead and look at the list. I'll put the list up on the screen. Look at the list and pick some of those that you think are not applied forces. Any of those that are not applied forces, pick them out and try to figure out, try to be able to explain why. Okay, we're back. Let's go through that list a little bit. Kicking a football. Kicking a football is absolutely an applied force. You're giving that football a force, you're kicking it, you're applying a force to that. That is totally an applied force. Spring force. Just to let you know, all of these I got from your answers on the questions to the Forces in Motion video. So I didn't make any of these up. These are all actual answers that I either liked or wanted to discuss with you. Spring force. That is an elastic force. That is not an applied force. That is an elastic force. Elastic force means anything that changes shape and wants to get back to its original shape. A spring is that right there. You pull a spring out, it wants to pull in. You squeeze a spring in, it wants to go out. The spring force is an elastic force. Now, some elastic forces, like this water balloon launchers, create an applied force. So this right here is pulling back. The force that wants to pull my hand this way is an elastic force. However, this cloth right here was putting an applied force on the balloon, making it go up. Hammer smashing something, absolutely an applied force. Hammer hits something, it applies a force on something. Yes. Pedaling a bicycle. When you push down on the pedals, that is an applied force. You are applying force to that, definitely. Now this one I had a little hard time with, dragging. Now, you could take this either way. And of course, a lot of these you can argue one way or the other. But dragging, if you talk about actually pulling something along, like this, in order to make this, in order to drag this cup, I need an applied force, correct? I need to apply force to it. But the actual dragging of this along the surface, that is friction force. So it depends on how they meant that. Dragging could be friction force or applied force. The pulling and dragging something, applied force. The rubbing against, definitely friction force. Magnets. Magnets are its own force. It's a group of forces called non-contact force. The non-contact forces are forces that do not touch things, that influence objects without actually touching them. Gravity is a good example of a non-contact force. If I go up in the air, nothing's grabbing me and pulling me down. I'm just being pulled down by this invisible force. Magnets are the same way, all right? A magnet will pull something, another magnet, towards it without actually touching it. Electricity is another non-contact force. So magnets are not an applied force. People walking, well, this kind of goes up along with dragging in that you could argue other things. Me actually pushing with my foot, the actual force of me pushing forward, I'm applying force to the road, making me go forward. That is it. Punching a wall, 100%. If I punch a wall, applied force. And centrifugal force. This is actually something I wanted to talk about. Centrifugal force is not an actual force in the sense that a force is a push or a pull on an object. Centrifugal force is not something being pushed or pulled. It is something wanting to go in a straight line, but it can't go in a straight line because it's going around in a circle. It wants to keep going in a straight line. Therefore, it appears, it feels like you're being pushed towards the center of the, or I should say, it's being pushed towards away from the center of the circle. That is, there's no force pushing you that way. If you're in a car and the car turns and you get pushed towards the outside, you're not getting pushed. You just want to go in a straight line, and the car is moving. So it's not really a force that is acting on you. It is more the result of motion, which we're going to talk about a little later. Okay, the next one is friction force. Go ahead and look at the next picture, the next slide, and tell me which of these is not an example of friction force. Okay, good. So you had a chance to look at them. I hope you have some in your brain and have some thoughts in your brain. Again, these were all given to me. I have to say that there's only one example of not friction force there. Skis on snow, friction force. Now there's less friction because of the wax on the skis and the snow, but there is still friction, all right? A lot less, and that's what makes it so fun. Makes you go fast, stuff like that, but there's just a lot less friction, all right? More friction than if I were to stand there in my boots on the hill, right? But still a little bit of friction. Going down a slide, yes, that is friction. Your butt rubbing against the slide is friction. Brakes on a car. This is how brakes work. Brakes work on friction. This is why brake pads heat up. They clamp on the brake cylinder and they stop the car with friction. Riding your bike on the sidewalk. You absolutely have friction here. If you didn't have friction, every time you pedal, your wheel would just spin. You pedal, there is friction from between the wheel and the road, and that creates an applied force pushing you forward. But yes, totally friction. Lighting a match. Lighting a match is taking a match, rubbing it against sandpaper. That heat created from the friction fires up that phosphorus tip, and the match lights. So yes, friction. Carpet burns are from friction. Anyone who's played on carpet, got a carpet burn, or played on artificial turf and got a burn, totally friction. This one, birds hitting birds, not friction. This is an applied force. When birds run into each other, now I've never seen that happen, might happen sometime. At one point, I think birds kind of have built-in mechanisms to prevent themselves from running into each other, but it could happen, and if it does, they are creating an applied force on each other. Now, if that said birds flying through the air, I could buy that, because you have the birds flying through the air, you have the sliding friction of the air going around them. Another thing we call that is wind resistance. And starting a fire with two sticks. That is 100% 100% friction. Friction that generates heat, enough heat to catch something on fire. That is friction. Okay? Now, the next question I want to answer is, how many times did Mr. E get hit by the balloon? That was a bonus question. If you stayed till the very, very, very end, you saw some outtakes where I got hit a bunch of times. And I'll show you a slide in just a second that is going to show screenshots from all 7 times. That's right, 7 times I got hit by a balloon. You can imagine my son had much, much more fun filming that than I did, throwing balloons at me. You could see he threw more than 7 at me. A couple of them missed. But that was 7 times getting hit by a balloon. Okay, so let's go forward. If you see over here, I have my table set up. I'm going to move the camera in just a second. I'm going to do a demonstration. No, I did not leave my table out, my dishes out from breakfast. I actually want to show you something here. So I'm going to move the camera and I'm going to show you something, and we will talk about it. Okay, You can see we have this lovely setup here, ceramic plates, nice silverware here. I'm going to try to remove the tablecloth without touching any of the plates, without moving any plates. I want you to make some observations of what happened, what's going on here. Make some observations. Ready? Go ahead and take a second, make some observations. Okay, so I wanted to talk about why this happened. First of all, some observations you might have wanted. The fork moved, okay? Plate moved a little bit, all right? It did move a little. It might have jumped a little bit. These things moved a little bit. I don't know if you could see the spoon, but the spoon moved also. Fork and spoon definitely moved the most. We're going to talk about why this happened, why this worked. Why does this trick work? In order to do so, I'm going to give you a little clue as to why it happened. And I'm going to do this trick again. However, I'm going to do it with paper goods. Okay. Here we go. Set my paper goods up. And now you're probably already in your mind thinking what's going to happen. All right? Make some predictions. What's going to happen here? Is this going to work better or worse than the original setup? Not too bad. We have the cup and the bowl here, but the plate and the silverware, not so much. All right? So why is that? This is what we're going to talk about. Okay, the very first thing you need to know is fact number one is friction resists motion. Okay? Friction resists motion. Now, you already knew this. This was in the last video. Why does this help us out? What does this do for us? Well, if I pull this, we see it's moving. Mr. E, I thought you said friction resists motion. Remember, motion is relative. So relative to this tablecloth, this is not moving. It is resisting motion. It is not sliding around here. All right? Remember, motion is relative. If you take from if there's a little guy standing here on the tablecloth and I did this, he would tell me that bottle is not moving. So friction resists motion of this bottle on this paper, all right? So friction is going to pull these things off the table. This is why the trick is so, this is why the trick is so good, works so well. It's because you think that these things are going to get pulled off the table. However, here's some things. First of all, look at the fabric I used. If you can see this closely, this is nylon. What is one property of nylon? Very slippery, okay? This stuff is super slippery. So we are seriously reducing the amount of friction, all right? A lot less friction here. All right, so friction resists motion, but if we reduce the amount of friction, we can slide this out and it will not reduce the motion relative to the tablecloth, like that. All right? The next fact that you need to understand is an object at rest will stay at rest, and an object in motion will stay in motion. This is known as Newton's first law. All right? You guys know about laws. We've talked about laws in the past. We've talked about the law of superposition, the law of original horizontality, the law of faunal succession. These are things that scientists saw over and over and over and over again, and they said, look, guys, this is just how it is. This is the rule. This is the law. all right? The law of, this guy Newton came along and made these laws of motion, and he said that objects at rest will stay at rest, objects in motion will stay in motion, all right? That means that if I take this and I put it there, it's gonna sit there forever and ever until a force acts on it. You need a force to act on something in order to create motion or to change motion. For example, I'm going to grab it and move it. Bam, I just changed motion because of the applied force of my hand. Same thing if I once I create a force and it starts moving, it's going to move forever until a force acts on it. Now this is the non-intuitive one, because here on this earth, everything stops eventually. I throw a ball, it falls, it comes to a roll. I move this, it's going to stop. That's because forces are acting on it. What forces? Friction, applied force, something might get in front of it. These are all forces that stop motion. Gravity pulls it down, slides along friction. If we were in space and I took this water bottle and I threw it, it would go forever and ever and ever and ever, never slow down until a force acts on it. All right, and Isaac Newton came up with this. This is very intuitive. He didn't have access to space. He didn't try this out. He came up with this through math and through his careful observations. When they go to Mars, they take the rocket, they aim it at Mars, they put the rockets on, and they turn the rockets off once they get the speed, and that sits there and drifts for days and days and days until it gets to Mars. Okay, now once it gets to Mars, how does it stop? Well, it's going to stay in motion until a force acts on. They take the rocket, they shoot the rocket this way, or sometimes they turn it around, shoot the rocket this way, slow it down. Okay, it's the only way to do it. You don't have to, like in a car, you have to constantly press that gas pedal because the air's slowing you down, the ground's slowing you down. In space, don't have to do that. All right, so now, a couple things about inertia. I haven't said the word yet. This concept is inertia. This ability to want to stay at rest or stay in motion, this is all called inertia. All right? Now, a couple things about inertia. First off, I have two bricks here. Now, you guys all have an innate a sense of physics inside you, because I'm going to ask you a question and the answer is obvious to you. I have here a regular brick. This is a clay brick. Pulled it up from my patio. This is a standard brick. This is a piece of styrofoam. Same size, same volume, piece of styrofoam. Okay? Now, here's my question. Which one would you rather get hit in the head with? All right? The answer is obvious. This one here. Why? Well, because of inertia. This guy's much heavier, more mass. More mass means more inertia, meaning this guy is going to be harder to get moving. So in order for me to throw it at your head, I'm going to have to use a lot more force because it has more mass, same size, but more mass. So I have to use more force to get it moving. And once it's moving, it's going to need more force to stop it. All right? This is a property of inertia. This is what inertia is. This guy here takes very little effort to move it, and once it is moving, it take a lot of force to stop it. Therefore, less inertia. All right? Objects with more mass have more inertia. All right? Now, a couple of things about inertia I want to go over. First off, here is my Lego guy. Here is a car. All right, this is one of those cars that you pull back, you let it go, and it's going to go forward. I hot glued a little Lego to the top there, and I have our Lego hero here. This guy, he's wearing a crash helmet. Don't worry, he will be safe. I'm going to put him on the car just like he naturally does. I'm going to pull this car back. It's going to go jetting this way, it's going to hit the block. All right? So this car is going to keep moving forward until a force acts on it. That's the applied force of the block hitting it, or it hitting the block, however you want to look at it. Let's watch what happens to the guy. All right, what happened to him? Let's do that again. What happened to our guy? Well, there was no force acting on him, okay? There was nothing keeping him here, maybe a little bit of friction of him staying here, but when this car kept going, there's a force acting on this to stop it. This guy wanted to keep going, so he kept going and fell eventually off the table. This is inertia. He wanted to keep going in the same direction until a force acts on it. Now, eventually, gravity pulled him down. He slid along the table, along the floor, and eventually he came to a stop. But it took a force to act on him. This is what happens in a car. When you're in a car, when you put the brakes on, you feel yourself going forward. There's no force pushing you forward, all right? There's nothing pushing you forward. The car is stopping relative to the car around you. You are moving forward because you want to keep forward. The car is stopping, all right? Now, hopefully, if the car stops suddenly, all right, which I hope never happens, but if it does, this is why we wear seat belts, because I'm going to keep moving until a force acts on me. If that force is the dashboard, no good. All right. If that force is the seatbelt distributed over my lap and over my chest, all right, much better. Not to mention the airbags everywhere that are going to cushion. This is going to help us out. All right. We'll talk more about distributing forces later in a later video. But the bottom line is, this is one example of inertia. I have another example of inertia right here. This is my inertia device right here. Tried this yesterday, it didn't work great. Let's see if it works better here. Let's see here. I'm gonna put it like this. All right, I have two masses here. They happen to be oranges from my orange tree. I have plenty of them, so I figured I could spare two. I'm gonna take this and I'm gonna, not too bad, huh? Ready? Oh, I bumped it a little bit. All right, now there is a little bit of friction up top here. There is on my headphones. This thing is rubbing, so it is moving a little bit. But because these things want to stay at rest, there's not enough friction to move these things. So therefore, I can do this, and they will stay put. All right, ready? All right, you get the idea. So, object at rest will stay at rest, object in motion will stay in motion, and friction. These are the two things that you know so far. So, we're going to put them together right now. The last thing that I want you to know is putting those two together for the tablecloth trick. If we have the object here, we have friction pulling it this way, keeping it not moving relative to the cloth. We have inertia saying, don't move until a force acts on you, don't move. The question is, how much force is acting? Well, with a slippery cloth and kind of a round bottom and a very quick pull, we get very little friction and good amount of inertia. So if the inertia is greater than the friction or the force pulling it this way, then that object is going to stay there. So I'll say that again. If the friction of the object, okay, is slow, and the inertia is low, I should say, and the inertia is high, we're going to get motion. Now, let's go on both sides of that. Here's a cup. Cup, very little inertia, okay, much less inertia than this guy. So what happens? We get movement there. Still a good amount of inertia because this is so slippery. And remember, because this has so little mass, so little weight, it's not pushing down, less friction. Very little friction there because the more it pulls down, the more friction it's going to have. So this, it works, but you could see the cup move a little bit. All right? Now, what about this? How about we go here? Here's what's going on here. More friction. You have a whole big surface here of rough, like friction creating surface. And so therefore there's a lot of friction. However, there's a lot more inertia, more mass, more inertia. So what's going to happen here? Inertia wins. Still plenty of inertia. Why? A, I'm pulling it quickly, therefore minimizing the friction. B, I have a slippery cloth. If I did this on carpet, okay, probably not the same. Probably pull that brick right off, creating more friction. All right? That's all I have for now. I showed you 3 demonstrations about inertia. I showed you the Lego guy in the car, all right, wanting to keep going. When the car stopped, I showed you my oranges on my head, staying still while I move around, all right, and I showed you the tablecloth trick with the tablecloth trick, pulling the tablecloth out. Here's my challenge to you now. You have to show me inertia. Come up with your own inertia demo. You could research it online. You could do whatever you want. You could recreate something I did here. But what you want to do is you want to go film it, send it to me, or submit it on there's going to be an assignment on Google Classroom. It's called Inertia Demo, or create your own inertia demonstration. That's what it's going to be called. And you're going to film it and submit it in that. If there's no more questions, don't forget your STEAM project worksheet. Turn that in as soon as you can. Any questions, please email me. Have a great spring break. Bye-bye.